Hi, I'm Richard Freudenberger. I work at the farm here, and we've been collaborating, John Nelson, myself, and Johnathan, on getting part of this done. But part of my reason and collaboration here is we're going to be working with a pond circulator to help get the water moving within the body of water that we were looking at today. Then there's reasons for that. I mean, just the circulation of water is important, and there are reasons that I'm going to ask Johnathan to explain, because he's better at explaining, knows more about that part than I do. But what I'm going to talk about for a little bit, not for too long, is we have several options of stirring that water up and moving it in the direction. We basically want to take it from the bottom and create a pattern that will remove, basically reverse the situation. Take cooler water from the bottom and some of the material from the bottom and stir it around up to the top. And we're going to talk about several ways of doing that. One, it would be wind power, and the other would be solar power. And after we finish a little description of this particular image here, we'll get into that, and I can describe a little bit about what we need in the way of power, how fast the thing has to turn, what kind of but what kind of situation you're looking at as far as how far can you go with the wind, when do you need to think about the solar, how expensive it might be, what the requirements are, and some of the design elements of the very simple pumping mechanism that we came up with to make it happen. But I'm just going to let Johnathan talk a little bit about the thermocline and the situation in the pond before we get into the machinery, if you call it that we'll be using to get this accomplished.
So this is a pond in a pretty natural state for these days. And maybe 100 years ago, it was perfectly healthy. But now we have more atmospheric nitrogen from cars coming in, industry coming at it. We have runoff from agriculture, such as, we've already discussed one person who has a pond with soybeans and corn. Here we have horses, adding nitrogen and phosphorus. So now the pond can no longer manage its nutrients. It's just like if we go and, if we were eating vegan and then we go to McDonald's and have 27 Big Macs, that's the state of this pond. It's just 27 Big Macs in. And so you got it's anaerobic, and it becomes eutrophic. And so there's no mixing of it, and basically the low oxygen layer gets larger and larger, and the part that has oxygen gets smaller and smaller. And then at night, but the surface is maintained during the day by the algae because they are photosynthesizing. But then at night they stop photosynthesizing for some reason. I don't know why they'd stop at night. I'm kidding, but because the sun's not shining. But then their cells start dying off, so that robs the oxygen out of the water, so you become eutrophic or dystrophic completely, and that's when you start to see fish kills in water. So you're getting a nutrient load on it, and then more. So what we had to do when we're looking at all bodies of water now, maybe 50 years ago, 30 years ago, but this area is becoming more settled. There's more stormwater runoff. There's more roads now. So ponds are getting more impact, and so I think we have to partner up with their natural systems and enhance their natural systems. And how I sort of explain to, like when I'm talking to my chiropractor or doctor about what I do, I was like, yeah, we just put vascular systems and kidneys and livers into ponds. And that's so, what we're talking about right now, what we built today was the kidney and the liver. And what we need now is we need a way of delivering the pond's life force to the kidney and the liver. And that's what Richard and I are talking about. So this is the unhealthy pond. And ponds usually do have a thermocline. And what I do, which is because a lot of the ponds I work on are just so, then this is a kind of brutal method, is I'm just pushing the water up, and we don't have a thermocline anymore. And we just continuously mix it, and that makes for a pretty healthy pond, but it's not a natural state of a lake. And so we're going to talk about this method, which isn't necessarily the worst case scenario, and other methods that are a little bit more, little gentler and a little bit more natural. And so I'm going to give the whiteboard to Richard here.
Basically talk about pumps, or the least technical kind of pumps there might be. Okay, this is a commercial model of more or less what we're trying to replicate. So what we have is, this is a solar machine. Basically, this is a draft tube and a floating, these are the pontoons, a floating frame here, and at this point here, not all the way down here, not in the middle, but at this point here, there's basically an auger, just like a grain auger, that lifts the water up, sucks it from here, and lifts the water up, and then it hits this. If you can see it, it's like a flanged bowl. We're hitting the bottom of that, and that's going to create water to just create a loop like this. On this particular model, the thermocline, which is that separation between the warm and the cold, is somewhere in the middle, and this is on a cable, so you can adjust it to meet the need. And in our case, we're not going to pull from that area. We're going to pull right from as close to the bottom as we can. So this is just sort of an example of what's going on. And on the top is two solar panels on an A-frame, and a battery is installed somewhere in here so that at night the stored energy from the daytime and sunlight time is utilized, and it'll still keep the...
And one of the most critical times to aerate a pond is between around midnight and dawn.
Oh.
That's when the dissolved oxygen is lowest. So that's why the direct solar doesn't always work as successfully, because that's when all the algae cells are dying off and taking all the oxygen out of the water, and that's when you'll get a fish kill.
Right. And the battery is just basically like a marine, like a deep cycle battery, probably a gel battery that can stand moist conditions. So it's just in a little. In this model, it's in a little pouch in that level, and it's not a huge battery. I think the biggest one was about 140 pounds. That is pretty big, pretty heavy. But these floats are, this is a pretty substantial piece of equipment. It's not actually on these bigger ones. It says do not dock boats, do not tie up here, because it's almost alluring to tie up there and maybe see what happens. They don't want to get near it. So, but that's just a model. I mean, it's just what we'll basically be doing is using the lower half of this on a much smaller scale in the range of maybe 10 or 12 inch diameter draft tube. We can use PVC pipe. If we don't want to use plastic, we can use a galvanized culvert. If we don't want to use the galvanized, we can maybe coat it with some kind of anodization or something, and it won't be chemically as bad. We could probably fabricate. We could use just mild steel, just regular pipe, or fabricate something out of our shop materials. But essentially, we're looking at a depth of maybe 12 feet in our case, probably. I don't know. We're assuming that we're probably going to plumb the pond and see how deep it is. We've talked about maybe it's 15 feet or so, but I would imagine that 12 feet in a 15-foot pond would probably be adequate.
There's actually a piece of electronics now where you can attach it to the back of a kayak and go back and forth, and it'll give you a bathymetric model of your pond.
Yeah.
It's not horribly expensive either.
Yeah, exactly. And that may be, maybe what we can do. So I just want to give you an idea of what it would look like, but it would be a lot less complicated than that. We'd probably just do a two pontoon kind of a device, and it's really pretty small. I mean, the draft tube being only 12 inches like that. So we're maybe talk about the size of that table, more or less the width. So this is essentially the auger flight. This is a typical grain type auger. I mean, it's a very broad bladed schedule of these things come in 5-10 foot sections or longer. You see them for grain elevators, and grain essentially is water is going to grain in its grain state is just like a fluid, and it's going to move just like the water would. The clearance, this goes in the tube, and the clearance between the edge of this, clearance between the edge of that and the outside tube is really going to be just half an inch or so. It's not close enough to hit. You don't want it to hit the metal. We're not going to use. We will not use the entire length. It is not an auger. It's only 2 flights of the auger, which is maybe 2. I mean, we'll see. It's probably about that. I have to still calculate.
If you rifted over the draft tube, you've created a vacuum. Yeah. So you started that motion already, so you just need to move a very small section.
Right.
And that perpetuates it just like an airlift pump would. But once you move that water over the top of the draft tube, then all of the head pressure of the lake is pushing it back in.
Yeah. So it just continues. It doesn't take much at the top to pull it all in. The other thing is that you would think that most of the action, most of the volume of the water comes up through the center. it actually doesn't. Some comes up through the actual center of the tube, and some actually comes alongside and what they call a laminar flow, and will come up and add to that substantially and create that movement. So we're relying on that. Now this does not spin fast. It doesn't need to spin fast. I'm looking at about 26 to 80 RPM, which is, in the world of motors and stuff is minuscule. And that's good because the first thing we're going to look at is a wind-powered device, which I have my reservations about because of the trees around here and the size of the pond. It's not like a 10-acre pond where you have a lot of surface area that the wind can actually pick up on. But we'll do some monitoring. I may hook up a little anemometer and do a little testing and see what kind of wind we get along the shoreline over the course of time.
I share your gut on wind in this pond.
Yeah, so that's why we're talking solar option too. But in many people's cases, that will not be the case, and the wind will be adequate. So we're not talking about, which is the next one? We're not talking about a traditional, it's a Savonius rotor. It's a very simple wind catching device that has a lot of drawbacks in normal electricity production. You'd use it to make electricity, but for our purposes, it's really much, much better. And essentially just think of see those two shapes? Just think of two 55-gallon drums, or one 55-gallon drum cut right in half lengthwise. And then you take the two halves and just butt them together in the middle. And that's essentially on an axis, on a vertical axis, so it can spin around. Now the problem with this, there's two problems with this. I'll talk about the problems first, then we'll talk about the advantage of it. One is it can only spin at the speed at which the wind flows. I mean, it's not going to go any faster than the wind flows because it just can't. It's a scoop, and it gets pushed, and then the next scoop takes over, and it gets pushed. So it unlike a traditional modern wind turbine, and I'll explain why in a minute, which can spin faster than the wind blows, this cannot. So we got that problem. The other one is that only 50%, essentially only 50% of the wind's force is going to be taken advantage of, because while you have wind blowing this way, it's pushing this one's actually pushing against the wind. But fortunately, since it's shaped like that, it's not like a sail, it's more like a wedge, and it's shoving the wind back. Now people with engineering and aerodynamic skills have actually weaseled this stuff around here. So these two, there's a little air, there's an overlap here, and air can actually transfer between there. So it actually helps prevent this from pushing being such a drag, and this one while this one's being pushed. So we're not, there are some mitigating things you can do to sort of improve that, but essentially it's extremely simple. It's at the speed we're looking at, at lower speeds it starts up and it might spin at 25 revolutions a minute, and at higher speeds it could get up to 80s, which is more or less we want to be in that range somewhere. The main benefit of something like this, other than its simplicity, is the fact that it starts up. It actually starts to spin at a much, much lower speed than any traditional wind turbine with blades that you might see in even the kind that we saw at the other farm we were at with the big multi-bladed thing. That takes not an incredible amount, but that takes a fair amount of wind to get it going. Once it's going, it can maintain its speed, but something like this, just really, really low wind speeds will start it, and that's really all we're asking. So, and then it's also very simple to make. So we have a rod goes through here, a shaft, a bearing either here and here, or on the shaft up here and on the shaft down there, and that would then operate the auger flight that we saw before. So it's all that simple. It doesn't really need to be any control. I mean, it just goes when the wind goes, and it stops when the wind stops. So this is just some incarnations of how this might be. You can see a little clearer picture of the the way the scoops would be. This is a little more complicated. It's multi-level. It's on a plate, and we have a couple of different sections of the scoops. And if you notice, they're offset a little bit. So one sort of ends here, the other one ends 1/3 over, and the other one ends 1/3. So there's always something facing the wind, and that may be. We have not come to a conclusion about which design I'm going to use, but we'll work it out. But these are all pretty interesting, and that's a stainless steel version of more or less what we're looking at with the bearing, the shaft, the bearing here, and the bearing there, and then the business end of it has the auger down there. So this will be on a platform, on a framed platform, and probably make it out of some. I mean, it could be wood, but we'll probably just weld up a little iron pipe deal or stainless steel pipe and just float it on 2 pontoons and keep it small, and that should be fine. I'm imagining a wind, something in the nature of maybe 6 foot maybe with.
Those old pond masters were about 4 feet, and they were they were incredibly effective at turning that little blade.
Yeah.
They just weren't very efficient at moving water because of what was at the business end of the.
Right.
But the rotor was pretty
Yeah.
good, and the frame. I mean, it lasted, New England winters.
And there's other. I think I have an image of.
There was a commercial product called a Pond Master that was available, and it was for de-icing water for livestock. But we used it to turn ponds over with some success. But it was just it kind of had a lawnmower blade at the bottom of it and no tubing. We could have modified it, thinking back now, and put in the draft tube. But it's just they went out of business, unfortunately.
Hit the next one. Yeah, that's another option possible. That's just something I grabbed off the internet, but that actually allows you to. That wasn't so much the cool bicycle wheels and all that stuff. What I was thinking of just you. Yeah, it is cool. Pretty much, you're taking the barrel and you're moving it, or the barrel scoops, and you're moving them out on outriggers. So you're getting an opportunity to use more surface area to scoop, to gather the wind. Now, if you go out, the further out you go, the slower it spins, but the more torque it has. Torque, it can. The speed is obviously revolutions per minute, but torque is the power in that turning. So we'll need to have torque and the speed range we want. So we have to think about that, and we'll adjust our design to achieve the best of both worlds on that scale. So we can go to the next one. This is just the typical this is the 350 watt. 350 watts is, think of 3.5 old-fashioned light bulbs. You got 300 watt light bulbs and a 50 watt light bulb, and that's all you could power with that at its maximum output when you got a good breeze. That just gives you an idea of scale. But just the nature of the design with something like this is an electricity producing machine. These blades are an airfoil design. The scoop is just like that. And there's really no aerodynamics to it other than it's a big spoon, and the wind is blowing into it, and it's gonna move it. Airfoil, looking from the end of the blade, if you held the blade out and looked down the thing, an airfoil, I'm just gonna sort of give the wind's 10 miles an hour, it can only turn it, at that speed. It cannot make it any faster. As the wind, in a blade like this, as the wind goes over the surface of it, it actually creates a suction. So the blade can spin faster than the wind is going. And if you use the right design parameters, you can get what they call a tip-speed ratio, a much improved tip-speed ratio. So a 6-to-1 tip-speed ratio is like really good, and with a well-designed blade, that can happen. This is a 1-to-1 tip speed. This is maybe 1-to-5, something like that. This is good for electricity, and that's good for what we're trying to do. So, we can't get aerodynamics out of this except for that little explanation I had before, where they're using that little air. Something's happening in here, so they're letting flow, help ease it through its circular motion. We don't have to worry about this unless we were using this to drive some kind of electric pump like we would, instead of using a solar panel, if you mounted something like that on the edge of the pond and then ran wires over to a electric drive to drive the auger, that would be the way to do that. But the solar is just so much easier. It's more compact. It's less maintenance. It fits right on the machine. So there's really no, the correlation, unless you had extremely good wind at the edge of the pond and you wanted to use something like that, that would be okay. Let's go to the next one. Another thing here, multi-bladed turbine like we have, aeromotor, and others. People make water pumping mills. They're really nice because they have a lot of power to them. They do take a little bit to start up, as I said before, and they're not made for really high speed, extremely high speed, because they can vibrate. In which case, that tail is designed to fold, and it actually hinges, and it turns the business face of the wind turbine away from the wind, so it slows it down. So it's self-regulating. But again, I mean, this would not be, if you put a gearbox on something like this and let it spin that auger at the speed we wanted it to spin, that would be fine, but it would sort of be overkill, because that can get sort of heavy. You have to build a bigger frame, a bigger pontoon section. There's a lot going on there. So, I think just the Savonius design and the auger is probably the way to go. We're looking at, like on something like this, you can calculate how fast the shaft is going to turn by the fact of how many feet. If this is a 4 foot diameter, then 3.14 or pi times that is going to be how many feet it's going to travel in one revolution. So if you have a 10-mile-an-hour wind, you'll realize you'll go that many feet times 10, and then we can figure out how many miles an hour, calculate from how many feet per minute into miles an hour, and then you realize we come up with revolutions per minute of about, it's at the estimated startup speed, it would be about 26 revolutions per minute, and at I think I picked a 12-mile-an-hour wind speed, it would be 80. And that's right in the range of where we want to be. Because if you go much faster than that, you're going to just be stirring up. I would think you just start cavitating, making bubbles, and and plus it probably wouldn't have the power to do that. It would pull this down and keep it at the speed that it just wanted to live at. So, this is the next one. Yeah, that's just an example of of a tower mounted on put it on a tower and by the edge of the thing. Is that the end of it?
Looks like it.
Yeah. Okay.